Okay, should I kick it off?
Yes, our first speaker is Emma Bailey from the Community Graduate Center, who will speak, as we see, on large deviations of Selberg's central limit theorem. So please go ahead.
Thanks, Mel. Yeah, it's my pleasure to be speaking here at CANT 2022. So as Mel said, I'm going to be speaking about some recent work I've been doing, which is joint with Louis-Pierre Argan here at CUNY. And it concerns essentially, I guess, colloquially, large sort of probabilistic statements about large values of the Riemann Zeta function. So I'll quantify that much more shortly, but I guess just as a overriding statement, this is the sort of thing I want to be studying. So from the title, Salberg's central limit theorem, as I guess any central limit theorem is, it's a statement about, I guess, typical values of random variables. And here, the random variable, which on the surface of it doesn't look random, but the random variable I'll create is the Riemann Zeta function. So I'll be much more precise about what I mean shortly. But since this is the first talk, let me I guess, lay some groundwork and some communal notation. So I'm sure this will be very familiar to many people, but perhaps not to all. So a brief introduction to the Riemann Zeta function. So the Riemann Zeta function is a function of, in general, a complex number S. But for certain values of S, this is going to be given by this infinite series here. Clearly, this is well defined, provided that the real part of S is still right of 1. So we have convergence. And it turns out that this sum can be written instead as an infinite product. So this product here is over primes P. And you can sort of see where this is going to be coming from. The local factors here are like the limit of some geometric series. And so by expressing these and using the fundamental theorem of arithmetic, you can go between these two forms here. So both these are well defined to the right of 1. And pictures, I find, make things more believable. So here's a plot of the Riemann Zeta function for real values of S from 1 onwards here. And so you can see the issues we're going to have at 1 with the divergence of the harmonic series. But nevertheless, you can analytically extend zeta to the punctured complex plane. So we're never going to get around this issue at 1, but more generally, we can create an analytic function on the whole plane. And so as an example, here's how you might start going about that. The details of this really don't matter. This is just some background. But here's an integral you can write to represent zeta. So you can see this part here is going to be where our polar S equals 1 is coming from. Okay, this is the fractional part of T. This really won't play into the rest of the talk. But you can see that this integrand, at least, this is going to be fine. We've moved ourselves. We can. This is well defined to the right of 0. Okay, you can keep playing this game and create an analytic extension of zeta. You can also create a functional equation. Yet again, the details of this really won't come into play for us, but just to introduce some concept of where the Riemann Zeta function is 0, it's useful to see the functional equation. This relates values of zeta to sort of mirrors of values of zeta here, up to this chi function. And okay, the chi function, the only thing I want to point out, has this sort of gamma times the sine function here. So the sine function is obviously going to deliver us lots of places where the Riemann Zeta function could be 0. The sine function is going to be 0 at any even number, any even integer here. But some of them will be cancelled out by the poles of the gamma function. So by staring at this, you can convince yourself that the Riemann Zeta function will be 0, certainly whenever we look at the negative even integers, exactly from these factors here. And because they were so easy to spot, these are trivial zeros of the Riemann Zeta function. So here's a little sketch happening here. So trivial zeros implies there may be non-trivial zeros, and that's a name given to any 0 that's not of this form, not an even integer. And again, from staring at that functional equation, you can convince yourself that the only other place these zeros could lie, this is the complex plane, is in this infinite strip here between real part 0 and 1. And the Riemann hypothesis states that any other zero that's not of the form -2, -4, etc., must lie at the center of this strip. So real part of S being a half. That's a Riemann hypothesis. And this is certainly a very hard question. I'm not going to opine much more on that. Okay, but much more tractable questions. So we're certainly still interested in the behavior of the Riemann zeta function on this, what's called this critical line, the line where we believe all the non-trivial zeros lie. So more tractable questions are questions like the following. So how does the Riemann zeta function behave typically? I mean, if you were to select a typical point on this line, so say pick some t, that is somehow typical, say how big is zeta, what's its typical size would be a natural question you might want to understand. And then kind of the other end of this spectrum, I guess, you could ask about atypical values, extreme values, very large values of the Riemann zeta function. So it turns out this is very related, but certainly a different question. So typical values versus very large values. These are other things we might want to understand. So this allows me to introduce the main theorem in the title of this talk. This is Selberg's central limit theorem. So a central limit theorem clearly is a probabilistic statement. So I need to introduce some sense of randomness here, because clearly the Riemann zeta function is deterministic. So how I do that is I want to introduce the randomness in the point at which I evaluate this function. So I could pick this, what I'm going to be calling a height, and this is a height because if we just go back to this picture here, I'm just going to think about picking some point, take some long stretch of this line and just pick some point uniformly at random in some big section of this line. And then the Riemann zeta function as a function of that random variable is itself a random variable. So now I'm going to use tau for when I'm doing this random selection. So for tau uniformly chosen between some large capital T and large capital T, Selberg's central limit theorem says the following. So it says that the log of the absolute value of the Riemann zeta function, notice this is the same as the real part of the log, clearly. So it's another way of saying this. So the log of the absolute value of the Riemann zeta function evaluated at this random point on the critical line. This tends to a Gaussian random variable centered with variance a half log t, where t is sort of the height at which I'm looking at my Riemann zeta function. So equivalently, obviously, I could normalize both sides. I could divide by the square root of the variance on the left-hand side, and then I converge to a standard normal random variable. So this is unconditional. You don't need to assume the Riemann hypothesis to prove this. And it turns out you can also have an equivalent statement about the imaginary part of the log. This statement also holds for the imaginary part of the log. Let me just look at the real part. So an equivalent formulation of this statement is the following. Let me just direct your attention to guess this line. This first line is just the exponentiated version of this event. So not really saying anything there. So just an equivalent statement of the central limit theorem, right, is saying that here's my random variable. I'm going to normalize by the square root of the variance and ask what is the probability that this is greater than some point v, some real number, fixed real number v. Well, this should be given by the CDF. This should be given by the Gaussian integral. And here it is. So this statement here, this is not conjecture, sorry, this is Salberg's central limit theorem here. So it's saying that this should be given by this integral. So here's the Gaussian density and should be given by the integral from v up to infinity. So you can see that this is saying about typical values of zeta, or values of the real part of the log of zeta, lying around square root log t. So this is telling us how the log of zeta behaves on scale sort of square root log t. Or equivalently, how the Riemann zeta function itself is behaving on this sort of scale here, e to the square root log t. And again, pictures can be helpful. So here's just a histogram I created. So I've taken, so height around 1 million, and I've just sampled this random variable 10,000 times, this tau, and plotted the evaluation of log of zeta at each of these half plus I taus. And here is this histogram here. So you can see, Okay, this is not so, this really should just be a heuristic graphic here, but you can see we're essentially centered at 0 as predicted. So it should be, well, it should be behaving like a normal random variable centered with variance essentially a half log a million, which is approximately 1.3 or something. So hopefully that's believable from this histogram here. There should be some sort of Gaussian behavior happening. Okay, so that was sort of an overview of zeta and what happens typically for zeta. So moving on to, so I want to be talking about large deviations. So what happens when you move away from typical zeta? So the question I'm asking here is what happens when you look far into these tails? So you look further than the central limit theorem is can hold. So you'll notice here with the central limit theorem, I'm only allowed to look at points V, so points into this tail V here, that are fixed. They're not allowed to grow with t. So not allowed to look any higher than scale square root log of t in the central limit theorem. So the question is, does this Gaussian behavior still hold if you do allow V to grow with t? So I'm going to quantify that more precisely. So the question is, does this Gaussian behavior, i.e. can we still model by this sort of Gaussian CDF type thing, does this behavior extend far into the tails? So what happens if you look on V growing with t? So in order to make this more precise, let me just introduce very, very standard probabilistic inequality. So that this, okay, what is this left-hand side? This is the probability that a standard Gaussian random variable is bigger than V. Okay, so I'm meant to normalize by square root 2 pi, but let's forget that for the time being. So this left-hand side is essentially the probability that some standard random variable, Gaussian random variable, is greater than V. Okay, so I'm not going to lose anything if I times by, well, I create an upper bound, certainly if I times by u over v, because u is always greater than v. But that makes this integrand integrable. And so I get this very standard Gaussian tail bound. So saying that this probability that a standard Gaussian is greater than v should grow no faster than this sort of shape of bound. So you see this kind of Gaussian factor here, and you have a 1 over v factor as well. So to quantify the above question, i.e. does the Riemann zeta function, is it still Gaussian in the tails? I want to be determining is a statement like this true? So is it true that, here's my random variable, the real part of log of zeta, and if I normalize that by the normal variance, now if I look into a point that grows with t, so v is now going to depend on t somehow, is it still true that I get this sort of bound here? So an e to the minus v squared t over 2 and then this factor 1 over v. So if that holds, then I say that the Gaussian behavior still holds into the tail. So this is the right tail that I'm looking at. And what would this tell me? This would tell me information about log of the Riemann zeta function near this point here, v of t times square root log t. So however v is growing with t, that would tell me information about zeta on this scale. So that might be motivation enough for people. So it certainly is a very natural probabilistic question to ask. But we might want to think, okay, well, what sort of scale are we really interested in? What sort of scale are we interested in looking at zeta on? And so one motivation is going to come from another very famous conjecture. So one is certainly extremely interested in determining how the moments of the Riemann zeta function grow. So this is not the log of zeta, this is, honest goodness, the moments of the Riemann zeta function. So this is a very famous conjecture here. So this is saying that these are the moments of the Riemann zeta function still on the critical line. This is a 2kth moment here. And the conjecture is that as you go further up the line, so as you go higher, this should essentially behave, I'm going to, whilst there's a lot of very interesting things to say about the leading order coefficient, I just want to focus on this order of growth here. The moment should grow like log of the height t to the power k squared. So this is a famous conjecture, and again, it's exceedingly difficult. Let me just comment that this actually hints as to why we might expect Gaussian behavior to be associated with zeta. So these are the moments here. So I'm not going to do anything on the left-hand side. I'm just going to exponentiate zeta. So e to the 2k log zeta certainly is zeta to the 2k. Just going to be lazy and drop this notation, half log half plus it. So certainly this is trivial equality happening here. This is conjecturally, by the conjecture, this grows like something like log t to the k squared. But again, I'm just going to do something trivial rewriting of this right-hand side. What is log t to the k squared? Well, it's this whole beast here. This is e to the 2k squared times half log t. So I've written this in a convoluted way, but the reason I've done this is this right-hand side here is exactly what you'd expect if you were taking the moment generating function of a Gaussian. So this is the form of a moment generating function of a Gaussian with variance half log t. So this is the exact form of a moment generating function of a Gaussian. And you can see here, this is again the form of a moment generating function. So this is sort of, again, hinting at why you might expect a central limit theorem to hold. So some very brief backgrounds. We know the moment conjecture for the second and the fourth moment. So it's work of Hardy, Littlewood, and then Ingham for the fourth moment. And you can see these are growing as you'd expect. So half of 2 squared is 1, and half of 4 squared is 4. And so we can see the predicted order of growth. And we know no other moments concretely, but we do know various other things. Let me just highlight for the sake of time. We know, for example, a sharp upper bound, so an upper bound that grows like the conjecture predicts, though we have to assume the Riemann hypothesis generally for this to hold. So this is work of Soundararajan and subsequently Harper to get this upper bound. So this sharp bound says that the moments of the Riemann zeta function do indeed grow no faster than log t to the k squared, which was the prediction. So tying this back to my question about large deviations of the Riemann zeta function, well, how are sharp bounds like this proved? Well, the first step is to notice that you can write the moments in terms of, again, like a measure of high points. So it's not so hard to show that just by essentially a change of measure, the moments of the Riemann zeta function are exactly this integral here. We can see the thing to understand is the probability that log of the Riemann zeta function is greater than some point gamma. And this is exactly the type of thing that I was introducing earlier. So the Selberg central limit theorem allowed you to look at gamma order square root log t, but more generally here, you might want to understand other values of gamma. And it turns out, Sound proved that the main contribution to the 2kth moment is looking at gamma around k log t. So notice this is quadratically larger than Salberg allowed us to look. And so Sound in his paper on the moments proved the following, that this sort of probability of being large is bounded almost like we'd expect with the Gaussian tail. So I particularly want to focus on gamma around order log t, because that's where we want to be looking. And so he's able to prove this bound here. So just to highlight the comparison to what we'd expect if the Gaussian tail were to hold, well, we'd expect exactly this type of behavior here. But what we're missing in this result, this is log t to little o of 1, but actually what we'd expect is like a 1 over square root of t. That would be the comparison here. V is going to be like square root log t. Sorry, this should be a square root 1 over square root log t. So what we're missing in this result, so Sound proved this and Harper subsequently removed this, but we were still missing this decay here. And so in my last couple of minutes, this is what I want to highlight. This is what we've been able to establish. So myself with Louis Pierre, we've proved the following. So for gamma, exactly growing like the range in which you would want to understand the 2kth moment. So we have some restriction on which k's we're allowed to look at. But in this range of k, we have that the probability that log of zeta greater than some point gamma, or gamma's growing like this, is exactly following the Gaussian tail. So in particular, this is what we've been able to identify, this 1 over square root log t. And so as a final comment before I guess open up to questions, we restrict somewhat the gammas we're able to take. So you see K here has to lie between 0 and 2. This is because we don't assume the Riemann hypothesis. We want to avoid assuming the Riemann hypothesis, and this is exactly tied to the fact we only know up to the 4th moment of the Riemann zeta function. So you could extend this result if you assumed RH to essentially all positive real numbers K here, and you get this Gaussian decay here. So this is implying that the Gaussian behavior does extend at least into the right tail when you're looking at points on the sort of quadratically larger than Salberg allowed you to look. But I'll stop there and open up to questions. So thank you very much.
All right, thank you.